Yeah, and thanks everyone here in person and online for being here. I know the weather, especially for the people here in person today, is not so great, so I really appreciate it. Yeah, so today I will be talking about parallel tempering. For those who aren't familiar with parallel tempering, I will be doing a little intro to PT so that you get a little primer on it. For those who are familiar with PT, it'll be a nice review. Parallel tempering is a Markov chain Monte Carlo algorithm for obtaining approximate draws from a target distribution of interest. In my world, those distributions usually show up as Bayesian posterior distributions. And in sort of modern, challenging, high-dimensional problems, these distributions can be quite difficult to sample from for traditional Markov chain algorithms. And so PT sort of offers a solve for that to some extent. The particular, I guess, technical contribution of today's talk is some work that a PhD student of mine, Nikola Surjanovic, did on analyzing the convergence of parallel tempering. Of course, the convergence of Markov chains used in statistics is sort of an important thing to think about because it tells us something about the quality of the approximate inferences that we can obtain from the draws that we get. So without further ado, I will say that, so Nikola is the lead on this project. He's an excellent PhD student. This is joint work with my colleague, Alexandre Bouchard-Co, who is Nikola's co-supervisor with myself. And this is also in collaboration with Saifuddin Syed, who is a Florence Nightingale Fellow at Oxford University. Okay, so let's start from the beginning, just to bring everyone up to speed. In my world, most problems have the following sort of mathematical appearance. I have some data, I'll call that X. Because I'm doing everything in sort of a Bayesian world, X really won't make much of an appearance throughout the talk. I'm going to assume that it's fixed, our data, throughout the talk. And I have some unknown parameter theta of interest. Now, in real applications, theta can be a very complex object. It could be a phylogenetic tree, it could be a graph that I'm trying to understand, it could be some weird discrete matrix structure, but for the purposes of this talk, I'm always going to do illustrations in 2D so that I can put them on the slide. So in this case, I've got my example, theta 1, theta 2, two latent variables, real values that I'm particularly interested in. And as a Bayesian, I want to characterize my uncertainty in theta. And so I'll start before I've observed any data by specifying a prior distribution on theta. So that characterizes my uncertainty that I have in theta before seeing data. I'll call the distribution and the density function sort of interchangeably pi naught throughout the talk. Sometimes I'll refer to that as a reference distribution. As you sort of dig into parallel tempering more, you'll see that the reference doesn't actually need to be the prior. They can be different things, but for this talk, I'll keep everything as simple as possible, and I'll use the term prior and reference sort of interchangeably. So you can see that I've drawn some density contours there. For the purposes of this little cute example, I'll say that my prior is an isotropic Gaussian. Okay, I get some data. I incorporate that data using the usual mechanics of Bayesian inference, and I get a posterior distribution, which is an updated understanding of what theta is given my data X. In particular, it's the conditional distribution of X given, given theta given X. And I've drawn my little blue density contours there as the updated distribution. Throughout the talk, I'll call that the posterior distribution, pi 1. Pi 1 is kind of the distribution we really care about obtaining draws from. And indeed, the goal of a lot of what I do is to estimate expectations under that posterior distribution, pi 1, usually through obtaining draws or approximate draws from that distribution. I'm interested in estimating things like posterior means and variances, tail probabilities, etc. The big constraint is that we are only given the ability to evaluate pi 1 and pi naught, my posterior and my prior, point-wise, and only up to an unknown constant. So given that constraint, what do people in Bayes typically do? Well, we can't exactly take draws from a posterior, so we have to do something else. One typically would design a Markov chain for which the stationary distribution is pi 1. It's that posterior distribution of interest. I run that Markov chain. So I start somewhere in my parameter space, theta 1, theta 2 in this case, and I run that Markov chain. And if I close my eyes and I just let it run for long enough, my probability distribution on where that state is of that Markov chain converges to my posterior distribution, so that when I open my eyes, the state of the chain looks like a draw from the distribution, as long as I wait long enough. In practice, we don't do that. We usually just run the Markov chain for some amount of time. We throw away the first fraction of samples, let's say 50% of draws. And then we ignore the ordering on the remainder of the draws. We sort of forget that we simulated this from a Markov chain and treat those as approximate draws from the distribution. The key property that we need from the Markov chain is that some notion of a divergence or a distance between my marginal distribution of my Markov chain state and the target converges to 0 as my computational effort goes to infinity. In this talk, I'll always use the total variation distance to characterize that distance between distributions. Okay, and we don't necessarily just want that the total variation goes to 0. We usually want that it goes to 0 quickly. In particular, we often hunt for geometric rates of convergence. In the literature, this is called geometric ergodicity. Sometimes, depending on particular definitions, it can be called uniform geometric ergodicity. I'm not going to make that distinction in this talk. I'm just going to say geometric ergodicity. And what I mean by that is I want the total variation after t steps to converge geometrically with some rate rho that's between 0 and 1. Why do we care about geometric ergodicity specifically? Why are we looking for this kind of rate? The reason is that in general, it implies a law of large numbers for the sets of approximate draws that you get from the Markov chain. And not only that, so that sort of guarantees that your estimates are asymptotically correct if you treat those as draws. You also get a central limit theorem, which tells you something about the uncertainty that you have or the inflation of variance due to the use of a Markov chain instead of a IID draws. The issue is that the usual sort of standard toolbox of Markov chain Monte Carlo methods like random walk metropolis Hastings, Gibbs sampling, slice sampling methods, etc., even Hamiltonian methods that you may be familiar with. They tend to explore the mass of the distribution well locally in small regions of the state space, but they don't always explore well the sort of global structure of the distribution. And this is particularly true when the distribution has sort of complex structure. For example, and this is sort of the canonical example that people tend to bring out when they talk about parallel tempering, but I think the next two examples are more compelling. But one is that if my distribution has multiple modes. So if I were to do something like a random walk metropolis Hastings or a sliced version of Gibbs sampling, for example, I would initialize my Markov chain somewhere in my state space, and it would walk randomly towards the mass of the distribution. And it might get trapped in one of those two modes, and it may have a difficult time jumping between the two modes. And so estimates that I get using my states from my Markov chain as draws will take a very long time to converge. It may still be sort of, after a long time, geometrically ergodic, but the rates might be quite slow. I think an arguably more common example that people don't often think about are distributions with varying scale or funnel shapes, for example. So when you design a Markov chain, often you have to pick a step size that sort of tells you something about what you know about the scale of the distribution. And you often have to tune that step size to achieve, let's say, some kind of acceptance ratio in your Markov chain. And so you may end up tuning your Markov chain to step well between part of that distribution, but it may not be able to get into the funnel, let's say. Indeed, the majority of the mass of the distribution might be quite far into that funnel. Finally, and this is a problem setting that motivates some of my work recently, is that in a lot of cases, your probability distribution is full support technically, but most of the mass concentrates around a manifold. And so when you run a Markov chain in that case, oftentimes you have to take these very small steps so that you don't jump off of the manifold. But in doing so, you make your sort of movement along the manifold surface to be. So in this talk, I'm going to propose parallel tempering as a solution to some of these issues. The idea of parallel tempering is to run Markov chain Monte Carlo not just on one distribution, but on actually multiple distributions simultaneously, with the goal of using the exploration of sort of easier distributions to help the exploration of harder distributions. For example, here's my multimodal target again. I'm going to keep reusing this example throughout the talk, so you'll see this multimodal example show up a couple of times. And that distribution might be hard to explore with a given Markov chain of interest, but if I just perturb that distribution a little bit, I might be able to make it a bit easier. So for example, I might perturb it by adding a little bridge of mass between those two modes. And I haven't told you how I'm doing this perturbation yet, but we'll get there. And then if that distribution is still kind of hard, I can perturb it again and maybe make the distribution even a little bit easier to explore. And I can keep going until I've got a distribution that's so easy that I can take IID draws tractably. So on the left, I've got what I call the reference distribution. I'll call that pi naught through the talk. And that, in this case, could be something like an isotropic Gaussian, something that we know how to sample from. Now I'm going to run MCMC on each of these distributions on this path, so all 4 of these distributions. I should make a little comment here. I've drawn these distributions sort of beside each other, but in your head, you should think of them as all being right on top of one another, right? So as I'm mutating one distribution to the next, I'm not shifting it horizontally. They're just sort of mutating into one another. I can't draw that on top of each other, so I'm splitting them side by side for each one. Okay, so I run my Markov chain in each one of these distributions. And that by itself is not so interesting. What is interesting is I'm going to start swapping states between the distributions. So I'm adding one more Markov chain move where I'm sort of moving information from the easy distribution down to the hard distribution. Okay, and so for example, hopefully I've got my mouse here, you can see that if I have a state up here, which may be not so hard to get to, when I swap it into this distribution, all of a sudden it's also in this very difficult to reach sort of isolated region of mass. Similarly, when I swap it into the target, now it's in a completely isolated region of mass. I've been able to explore by simply exploring a reference distribution. So the intuition here is that my Markov chain kernels are responsible for sort of local mixing. My path is what's pushing these draws into sort of difficult to reach regions of mass. Okay, so that's PT in a nutshell. We'll dig into the guts of it a little bit more in a minute. What I'll say for now is that there are fairly limited results out there. There are results. People have done some work on the convergence of parallel tempering. They have some drawbacks. For example, they depend pretty heavily on the details of the individual Markov kernels that you're using, which can be quite intricate. And even analyzing the Markov kernels themselves can be difficult, let alone a big ensemble of these Markov kernels. So we want to avoid that. Not only that, the analysis usually has constants that you can't estimate or you can't approximate in practice. So it's hard to say in practice what your convergence rate is given observations from your parallel tempering process. In this talk, I'm going to present some new results about the geometric ergodicity of parallel tempering. And in particular, we are not going to, or we're going to sort of, in some sense, assume away all the difficulties of MCMC and just leave the sort of critical piece for analyzing PT that is sort of mercifully simple to analyze compared to past approaches. A big win here is that our bounds can actually be estimated in practice. And I'll tell you about some software near the end of the talk that actually already is estimating everything you need to compute these bounds. So it's not too difficult to use our bounds and to understand what they mean. They're rather intuitive, and they pretty closely reflect what we see in practice from parallel tempering. I will say that in the manuscript that we're putting out soon, it's not quite on archive yet, but we'll get there. There are lots of other results that we have that I'm not going to have even remotely close to the amount of time I would need to cover today. All right, so I've mentioned these sort of cute little problematic cases for MCMC, and I've said, well, this is a good reason for parallel tempering. The first question that you should ask me is, well, Trevor, did you just make up some cute little problems for yourself? And are you just designing methodology for the sake of methodology? The answer is, of course, no. These kinds of structures exist in real problems. For example, multimodality shows up, both trivial and non-trivial forms of multimodality show up in clustering and sparse regression. Varying scale problems show up all the time when you use like sparsity-inducing priors with scale variables, for example, and hierarchical models for that matter. The case that sort of motivated me most recently are Bayesian inference problems that involve inference regarding things that are unknown about a differential equation of interest. Oftentimes, in those cases, you end up with this sort of noisy manifold structure. So to make that a little bit perhaps more concrete, I wanted to get more into the details of this because it's such a cool application, but I just don't have the time. So feel free to chat with me about it later. I'd love to chat your ear off about it. But I collaborate with some material scientists at UBC who are focused on the manufacture of composite materials. So think like carbon fiber or Kevlar, mostly for structures on planes. So like the wings of the plane. You know, getting right down to the crux of it without telling you all the details, they're interested in studying how these materials are cured in an autoclave. And the problem mathematically sort of boils down to inferring the boundary conditions of a big 3D coupled chemical kinetics and heat diffusion PDE with sparse measurements of the temperature of the system as it evolves. That's way too difficult to talk about right now. So I'll make a baby version of that problem, which is this. I've got a 1D heat equation on a rod, and I've got two boundary coefficients that determine the heat flow into and out of the rod. And indeed, actually, this toy problem preserves all the interesting structure of the big nasty problem. So I'm just getting rid of a bunch of engineering effort here. Here's an example of a posterior distribution that we get from all these problems. So I've got theta naught and theta 1. These are my two boundary parameters that I want to infer. I'm using a random walk metropolis Hastings kernel here. And you can see that the majority of the posterior mass exists on this sort of thin, almost line. So it's almost a low-dimensional manifold in 2D, but it's not quite. It's a bit noisy. And you may not even be able to see it on this figure, but if I zoom in, actually what I'm doing here, this little red speck, is my random walk metropolis Hastings. And because of the scale, the difference in scale between the sort of transverse direction and the in-plane direction, I really have to take itty-bitty steps for this thing to work reasonably well. With parallel tempering, we're going to start by, instead of trying to draw from this really hard distribution, we're going to draw from a much easier distribution. Let's say the uniform on the unit, or the length 10 square. Okay, so I can take IID draws from this distribution. This is a Markov chain that's mixing quite well. But if I can take draws quite nicely from this distribution, perhaps if I perturb this distribution just a little bit towards that target, I can still take good draws. So maybe I propose a move that sort of just shuffles those particles a little bit towards the distribution of interest. I can do that again, and I can construct this path of probability distributions for which I can take draws reasonably well. And at some point, I get all the way back to the target, and you'll notice a pretty big difference here in my parallel tempering Markov chain, which, by the way, the individual Markov kernels that are running in each one of those distributions are exactly the same as this one that was really struggling on the target by itself. We see that you get much improved mixing of this Markov chain. Indeed, you get much larger jumps along the manifold, which is kind of what you're hoping for. That's sort of I think, a pretty clear motivation for why we should care about PT. Let's dig into the guts a little bit of it now. So I'm going to define a path of distributions. Starting from pi naught, that's my reference, to pi 1, that's my target. I'm going to construct a path of distributions by taking essentially a geometric mixture of their densities. Okay, so pi naught to the power 1 minus t, pi 1 to the power t. I'm letting t range from 0 to 1. So at 0, I get pi naught, at 1, I get pi 1. Then immediately, because that path is a continuum, and I want to run an algorithm, so I have to discretize that path. So I will discretize that path to n plus 1 steps, starting at 0, t naught, t1, all the way up to tn, which is equal to 1. Now, instead of running Markov chain Monte Carlo on just pi 1, I'm going to run it on the product space of n plus 1 copies of the original parameter space. Okay, so I've got pi t naught, pi t1, pi t2, yada, 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 all the way up to pi tn. I'm taking a big independent product of these distributions. That is my new sort of augmented target for this big parallel tempering Markov chain that I'm going to define. So there's my example again. I've got pi t naught, which is my reference, going all the way up to pi tn, which is pi 1, that's my target. This is the case where n equals 3, so I've got n plus 1, 4 distributions along my path. And again, these are meant to be sort of on top of each other. I'm just spacing them out for visualization. All right, since we're running a Markov chain on the product space, let me instantiate a state for each one of these densities, pi naught, pi 1, pi 2, and pi n. Parallel tempering in this context has 2 steps. One is called exploration, and one is called communication. Exploration is a bit easier to cover, so let's do that first. In exploration, I'm going to apply a standard MCMC step to every one of the distributions on my path. Okay, I'm going to do this independently without any communication. So for example, I might use Hamiltonian Monte Carlo or something like this to sort of move each one of these samples around on its respective target and update the sample values as in that manner. Something worth mentioning is that because each of these MCMC algorithms is designed so that its individual pi tn is the target, then this obviously is invariant for the big joint distribution, right? I have independent draws, I perturb them by all these Markov chain kernels, I still have independent draws. The next step, so this is kind of the less interesting step of parallel tempering. The next step is communication. This is the more interesting step. Here we're going to propose swaps between neighboring states along the path. So for example, if I look at pi t1 and pi t2, I might decide, well, let's try interchanging those 2 states. Okay, so it looks like, again, it looks like they're moving left to right. They're just sort of changing the index. They're not actually moving. So I'll try swapping 1 and 2. Because I need to maintain the correct big joint invariant distribution, I have to use a Metropolis-Hastings correction here. So I'm going to accept this swap with probability alpha n. Remember alpha n, it'll appear again throughout the talk. Alpha n critically depends only on this function v of theta, not theta itself. V of theta is the log density ratio of the target and the reference, pi1 and pi naught. Okay, so we can make this acceptance decision depending only on v of theta, not depending on theta. That's actually a critical property for our analysis later on. I think that's a good introduction to PT. We accept that swap. Question, what do we need for PT to work well? If that's what PT is, exploration and communication, what do we need for it to work well? Well, we need exploration to work well, and we need communication to work well. Makes sense? Exploration, the job of exploration is to make sure that the chains mix locally well. So it doesn't need to make big moves, it just needs to make good sort of small moves. In past work on the theory of PT, there have been a couple of approaches to sort of mathematically capturing this. One is to partition the state space and say, well, my explorers sort of move around well within partitions. It's a perfectly reasonable approach. It's not my favorite because I don't often know how to partition a state space. And if you think of like those varying scale problems or like the noisy manifold, it's not clear what a good partition is to use. In the multimodal case, maybe it's obvious, right? You just separate the modes and say that my kernels mix well within modes. Another approach that people have taken is to assume that the exploration kernels are geometrically ergodic, which is not, for me, the most exciting characterization, because it basically assumes that, well, PT without communication is geometrically ergodic at that point. So you've kind of assumed the answer before you've even started the proof. Our collaborator Saf, in a previous paper, introduced another kind of assumption, which is that the kernels, after one exploration step, the potential functions v are independent. What this says is that the state itself, theta, doesn't have to mix necessarily well, but the potentials v have to mix well. Okay, we'll get into that assumption in a minute. The second thing we need is for communication in parallel tempering to work well. For this to be true, what we need is that there is significant overlap between adjacent distributions on the path, right? If I'm interchanging states between those distributions, they have to look similar. If they don't, I'll reject all of my proposal swaps. Once again, pulling from Saf's earlier work, something worth knowing is the global communication barrier, GCB, which is a function of just the reference distribution and the target distribution. And without maybe getting into the details of this integral, it's a path integral along the path of distributions. It really characterizes how much overlap there is along that path, right? So a large value of lambda means, well, it's sort of a long path in the sense that there's not enough overlap. A small value of lambda means that pi naught and pi1 are similar, and there's lots of overlap. So the GCB is you can almost think of it as like a divergence measure between two probability distributions that characterizes the length of the path from one to the other in some sense. So that's what we need. Now we're going to get maybe a little bit into the analysis itself that we do in this paper. So in particular, we need 3 assumptions for our analysis. Well, 3 major assumptions. There are some minor technicalities like support. The distributions all have to have the same support and things like that, that essentially always hold in practice. So I'm not too worried about those. The big assumptions are, first, that our reference distribution, that sort of easy one, provides IID draws. This, I should say, is not really a major assumption to worry about. In particular, we get to pick the reference in our algorithm. So we can simply just pick it to be something that gives us IID draws. And actually, in other work by Nikola, we optimize it. So we try to pick sort of the best reference within a tractable family. I will say that this is sort of possible, or I guess it makes sense because of the path that we use, pi naught to the power 1 minus t, pi 1 to the t. Because when you evaluate at t equals 0, you just get back pi naught, right? You need sort of the beginning of the path to give you good draws. In earlier work, people have considered different paths. So in particular, just pi 1 to the power t, which doesn't guarantee necessarily that you can get good draws when t is small. And not only that, I mean, that distribution may not even be normalizable, may not even be a probability distribution, right? It might be improper for certain values of t. The second condition we need is something called equiacceptance. So remember those alpha n's that I told you about, the swap acceptance probabilities? We need the average value of those, sort of on the long limit of running PT for a long time. We need those all to be equal to each other. That looks like a bit scarier of an assumption. As it turns out, it's actually not really much of an assumption either. In particular, we have a very simple tuning procedure that just kind of makes this true in practice. It's quite reliable. I'm very comfortable making this assumption without worrying too much about it. I should also say that this is not a necessary assumption. This assumption just makes our analysis a little bit easier, cleaner in some sense. The third assumption is the big one. This is the one that you should really sort of have alarm bells going off in your head about. Here we're asking that our kernel, our Markov chain, our exploration kernels are good enough such that the energies are independent. Okay, or I shouldn't say energies, the potentials are independent, the log density ratios. Why do we need these three assumptions? As it turns out, these three assumptions let us kind of ignore the exploration process, which is really the nasty, intricate part of PT to analyze. And what we're left with is just that nice sort of communication process. It's almost like a discrete Markov process, right? It's a process of chain indices. And so this is where that term exploration-agnostic comes from. So that we don't really care what our explorers are doing as long as these three assumptions are satisfied. So if you can tell me that a slice sampler satisfies these assumptions, we're good. Okay, let's dig a little bit more into that ELE assumption, because I think this warrants a bit more discussion. This is admittedly a big assumption, right? And you might wonder, am I asking for too much here? The question that we had that kind of scared us a little bit when we were first thinking about this is, does this assumption imply ergodicity of the explorers by themselves without even considering PT? Because if that's the case, then we may as well just go back to assuming the geometric ergodicity of the explorers. Luckily, the answer to this is an emphatic no. In fact, the ELE might be satisfied by Markov chains that aren't even irreducible, right? So a perfect example of this is a multimodal distribution with two identical modes. My Markov chain might go into one and be prevented from ever going to the other. But if as long as it takes draws independently within a mode, then the assumption would be satisfied. That being said, the assumption I don't think in any real practical example would ever hold exactly, right? Whether this is precisely true, I highly, highly doubt it. I think we think of it at least as an intuitive sort of simplification of the notion that what we really need from the explorers, which is that the V's are mixing quickly, right? Maybe we could replace this with a slightly weaker condition, like the V's are ergodic in some sense instead of independent. But I think for my money, this is the right way to formulate this assumption. I should say that even in challenging cases, the assumption, even when it's not true, it's sort of close enough to being true that we're happy with it. So for example, in a relatively challenging ODE parameter estimation problem, if I look at the lag1 autocorrelation of those potentials, so VT plus 1 versus VT, I get the following scatter plot. The autocorrelation here is 0.2. It's not 0. If it was actually independent, it would be 0. So it's not satisfied. But the conclusions of our theory sort of line up well enough with what we see in practice in this example that I'm actually reasonably comfortable with that amount of autocorrelation. So those are our assumptions. We've got IID draws from the reference, we've got equiacceptance, and we've got that efficient local exploration assumption. Now let's get into the sort of core technique. The basic result that I'm going to use is actually a very classical result from probability theory that says that if I have two random variables, x and y, that come from two probability distributions, mu and pi, that I can bound the total variation between mu and pi by the probability that x is not equal to y. So I'm free to choose the joint distribution of x and y however I want, as long as the marginals are mu and pi. And so in particular, I can design that joint distribution so that the x and y sort of coincide as much as possible. Okay, and as it turns out, for any such joint distribution, I get an upper bound on the total variation. It also turns out that there exists a coupling that makes that total variation equal. So there is sort of a best possible coupling. And we're going to use this to analyze PT. How are we going to use this? What we're going to do, and if PT wasn't complicated enough already, it's about to get more complicated. We're going to create two copies of parallel tempering, and we're going to couple them in such a way that eventually the last state, that target distribution state, will be equal. And then we're going to have a bound on our total variation by the sort of that basic result that I told you about. There are my two copies. All right, I've got my 4 chains again, top and bottom. The top copy of PT, that's going to be initialized at my target distribution. So this is the distribution that I actually care about taking draws from. These purple dots are the draws on the top, and they are independently sampled from each one of these targets. Okay. This is a hypothetical copy of PT. I can't actually do this in practice. The bottom copy of PT is the one that you can kind of think that's the one that I'm actually running in practice. Okay. That's initialized arbitrary. Our assumptions show up immediately in our analysis. So let's do our exploration step for PT, the very first step. We need to couple these 2 copies of PT. Because in the Explorer, due to the fact that I have IID draws from my reference, after a single exploration step, I can make the states in this reference chain equal one another, right? Because I have an IID draw. It's perfectly fine to just take one IID draw and just set both chains equal to that IID draw. That preserves the correct margin. Awesome. Throughout now the rest of this little example, watch that red dot. The red dot is the one that's kind of important to keep an eye on. I'll also say that due to the efficient local exploration assumption, all of the pairs of distributions that align with one another, they have the same potential. So V is equal across all of those, all the copies. But the actual state values, theta, may be completely different. Okay, so there's our exploration step. We've done exploration in all of them. I'm just highlighting the red one because that's the one that's interesting to look at. I'll say that my index process is the chain number for that red state. So right now it's at 0. So my index at time 0 is 0. Next, we're going to communicate. That's the next step of PT. And now, again, we have to couple these 2 copies of PT. But remember, because of that efficient local exploration assumption, all of the V functions across the 2 copies of PT are exactly the same. So if I make a decision about a swap in one copy, I'll make the exact same decision about the swap in the other. In particular, if I try to swap chain 0 and chain 1, if I reject that swap, both copies reject. If I accept the swap, both copies accept. So let's say they both accept. Now that red state moves over to index 1, and I can update my index at time 1 is going to be now 1. Now we're going to explore again. Let's keep an eye on that red dot. Because they are equal, when I apply my Markov kernel, I can just apply the same Markov kernel to both. That maintains the correct marginals. It looks like I'm running PT in each copy individually, but I indeed maintain that coupling of theta. And then we just repeat this process, right? We keep an eye on that red dot as it sort of bounces back and forth among the chains. Because it visited that reference state, it coupled. And so the 2 states will always be the same. Eventually, they'll make their way down to the target, and I'll have a coupling that I need. Theta prime n, which is my hypothetical copy, which has exactly the correct distribution, the marginal, is equal to theta n, and therefore it shares the correct margin. So at some point, my index IT will be equal to n. Okay, so in other words, using that cute little result from probability theory, I can say that at iteration t, the total variation between my hypothetical theta prime n, which is perfect, and my theta n, which I actually have in practice, is bounded above by 1 minus the probability that they're equal. And we know that if I go backwards in time, if I start at n at time t and I go backwards in time, if I ever touch that reference distribution, they couple. And so they must be equal now, right? So if I ever previously visited the reference, they're equal. The beauty of this is I can ignore PT now entirely. I don't care about PT anymore. I don't care about the states. I don't care if I have a phylogenetic tree or a graph or whatever. I simply have to look at my sequence of chain indices, and I can just analyze that. So let's maybe formalize that a little bit. That's the index process. So remember, when you watch that red dot sort of bounce back and forth, I'm looking at the chain indices for it. So I start at 0, and I start sort of bouncing upwards towards the target. I should say that on the y-axis here, I'm showing you the number of the chains. So this is an example of 30 chains instead of 4. And on the x-axis, I'm showing you time, so the iterations. Mathematically, IT is the index process. It's between 0 and n on the integers. VT is its velocity. So it starts in the upward direction 1, and maybe sometimes it can go down, can bounce, -1. I initialize at 0, my reference distribution, with velocity 1. And it follows the rule that it follows its velocity at time t. And if it ever reaches n, which is our target, it absorbs, so it just stays there. And if it ever goes back down to the reference, it reflects, so it starts traveling up again. The only randomness here is that my velocity v flips with probability 1 minus alpha. Remember that acceptance probability, the equi-acceptance condition. This is why it makes it easy, because I don't need to worry about a Markov chain that has sort of state-dependent acceptance probabilities or velocity flips. I can just do it constantly. But indeed, you could analyze this again with different alphas. Okay, so if alpha, that acceptance probability, is close to 1, then v usually stays the same. It usually doesn't flip, and so we get very consistent trajectories to the target. So it takes very little time. If alpha is close to 1, then v constantly is flipping, and I get sort of a diffusion of that index process towards the target. So it takes a long time. And just to make this concrete, we have a bound that says that the total variation in our target chain at time t is bounded above by 1 minus the probability that the index made it to the target at any point. So I've sort of converted that. I'm looking backwards in time to see if I ever touch the reference to just a purely forward Markov process. So this lets us stop for a moment and do our first result. The index process I've now sort of characterized as a finite state Markov chain with a transition matrix. Welcome to Markov chains 101, right? I can compute the probability that I'm in that absorbing state directly without worrying too much about it. Indeed, we have that the total variation at time t is bounded above by 1 minus u transpose a to the power t times v, where a is precisely my Markov transition matrix for this discrete process. A depends on the number of chains n and the acceptance probability alpha. U and v are indicators for my initial state and my absorbing state, right? That's where I start, where I want to evaluate the final absorbing probability for. Wonderful. That looks like it's geometrically ergodic. I guess I have to worry about eigenvalues of A, figure that what's going on there. It's kind of tricky because the rate is not totally clear. It's not totally clear how the eigenvalues depend on n and alpha. We've tried to analyze that. It's not trivial. A is not sort of a simple looking matrix. It's got lots of weird blocks in a lot of places. So it's not clear how the properties of A are related to pi naught, pi 1, and n, which is kind of what we care about. But this result does match our empirical results quite well. So for example, I did a little simulation experiment, or rather I didn't, Nikola did, shouldn't take credit for Nikola's hard work. A 4x4 easing model, so that's got 65,000 discrete states. To estimate the total variation in this example, we were using a Gibbs sampler, a typical Gibbs kernel. To estimate the total variation, we had to do 100,000 runs of parallel tempering and MCMC as comparison. So we start from scratch, we run up until iteration t, we record the state, we start from scratch, we run up until iteration t, and that gives us a sense for what the actual distribution at time t is. And then we compared that to our theoretical results. So on the y-axis of this plot, I've got the log 10 of the total variation distance, and on the x-axis, I've got the number of iterations. So of course, geometric ergodicity should look like a line on this plot. The first thing to note is that the parallel tempering finite chain theory actually captures our empirical rate quite nicely, right? And this is a case where the ELE assumption clearly was not satisfied. So there's our theoretical result in blue. You can see that we're decaying at some reasonable rate. The orange is the empirical version of this. We're off by a constant, but that usually doesn't matter too much. What we really care about is that rate, and we've seemed to have more or less nailed. The Explorer alone is in green, so that's just standard MCMC. As you can see, it doesn't work, right? So this is more evidence that PT is doing some heavy lifting for us here in this problem. That weird step pattern that you see, that's because we use a communication scheme that we swap all the even pairs of chains and then all the odd pairs of chains. And so the target only really changes once every other iteration. So you get a constant TV every other iteration, basically. And as I said, we kind of want to go beyond this, even though these results are quite nice. We want to go beyond this because they're not mathematically clear. It's not intuitive. I don't know a priori what this rate would look like. So to get from this computational result to a more sort of mathematical result, we actually do this weird thing where we look at the continuum limit of the procedure as the number of discretization points goes to infinity. So the number of chains, in some sense, the number of parallel computers that are working at the same time need to go to infinity. So what happens is our index process, which was this discrete state Markov chain with I going from 0 to n, becomes a continuous time Markov process. But otherwise, it looks very similar. So I is now between 0 and 1 on the continuum. V is still, the velocity is still -1 or 1. I has velocity V. I bounces at 0 and it absorbs at 1. 1 represents the target. In this case, 0 is still the reference. And instead of V sort of flipping with probability 1 minus alpha, now it flips with a Poisson process. And the rate is lambda. And if you remember earlier in the talk, lambda is the global communication barrier. It measures sort of a divergence between pi naught and pi 1. And so indeed, if lambda is small, if the global communication barrier is small, then the velocity doesn't flip very much, and we get these nice linear paths towards the target. It converges quickly, and vice versa. Let me call tau the hitting time of 1, so that's when that absorption happens. We prove an extension of this finite chain result to the continuum case, and this involves actually a little bit of sophisticated machinery. But ultimately, we show that the total variation at time t, but scaled by n. So you can see that I've got nt there now, right? Because it just takes longer to get to that target as I make n larger. But the total variation at time nt is bounded above by the tail probability of that hitting time of the continuous process. So this is the analog of the previous result in finite state. Why do I want to do this continuum limit? As it turns out, we can analyze this tail probability, and I have some slides afterwards that I can show you if you're interested, where that tail is given by the solution to a linear second order PDE. And the solution of that PDE we can bound. And that's indeed how we do this analysis. And it's not obvious from this slide how that's the case, but it's kind of a couple pages of technical detail. So you'll have to suspend your disbelief for now, I suppose. Okay, and here is sort of the main result of the work. Assuming a technical conjecture on a particular complex function of interest holds, the conjecture is of the following form. It says something about the pattern of poles and zeros. The function f is well known. It's actually simple to write down, but it's not trivial to analyze. And when I started hearing that we were trying to prove things about the locations of poles and zeros in a complex function, it kind of screamed the Riemann hypothesis to me. And I said, let's not do that for now. Maybe we'll just make that a conjecture. We've evaluated it to a great degree computationally, and I'm fairly confident that the conjecture is true. But maybe a more talented mathematician than myself can take a stab at it and see if they can prove it. Okay, but if that holds true, then for lambda greater than or equal to 1, in the case where lambda is less than 1, we have other results that are kind of simpler to prove. The hard case is when the GCB is high, when there's sort of a lot of friction between two distributions. Then we have that the total variation, again, in the continuum limit, is bounded above by a constant c that depends only on the global communication barrier, times x of minus t, essentially, over 4 lambda, again, communication barrier. So in other words, you would expect roughly n lambda steps to go from the reference to the target. Some commentary here. So first of all, this is shown geometric ergodicity in this continuum limit. This result is quite nice because that bound depends only on lambda, which is something that's actually quite intuitive, and it's something that we can estimate in practice. I'll get to that in a second. I will make some comments here. This 4 lambda should just be lambda. We definitely lost 2 factors of 2 in our analysis, and I know exactly where we did it. And so we're working right now on trying to gain back those 2 factors because it's clear from the empirics that it should be 1 over lambda. Now, okay, how much you care about a particular constant is up to you, I suppose. We were able to prove that C lambda is lambda cubed. It's not lambda cubed in practice. It's actually more like a constant. It's roughly 1.02, even for really large values of lambda. So our bounds there leave a lot to be desired, but at least it's polynomial. In other words, this is still sort of reflecting a good geometric rate in T that we're hoping for. As I said, it's easy to estimate lambda. Remember those acceptance probabilities? They're back again. The way I estimate lambda is by taking the empirical average of all those acceptance probabilities, actually rather 1 minus, so the empirical average of the rejection probabilities, and I sum them up over all the chains. It turns out that's a really good estimate of lambda. And as n goes to infinity, that becomes exact. And the error is something like 1 over n cubed. So it converges very quickly. You may also wonder, well, okay, what values of lambda do we have in practice? Do I need t to be quite large? Saf did some work previously that did a very comprehensive examination. And let me just highlight this last column. So suffice it to say, it's a lot of problems. Some of them are very hard. Lambda tends to take values in the order of 10, let's say, at most. So it's really not too bad. Even a spectacularly hard problem like this phylogenetic inference problem with almost 200,000 dimensions has a lambda of 88. So even then, we're not doing too bad. We expect lambda scales roughly like square root of the dimension of the problem. One last final simulation experiment. We compared, in this case, the finite index process to the infinite index process to see if our bounds are actually reasonable. This is when we realized that we were losing a factor of 4. Let me just use an example of lambda is equal to 4, and alpha, my acceptance probability for the finite chains, is 1 minus lambda over n. 1 minus lambda over n is the asymptotic alpha that you would expect to get, so we just set it that way. And indeed, my asymptotic slope in this case is minus 0.02. As a function of the scale time, I've got log 10 of total variation on the y-axis. And if I actually take n to infinity computationally in my finite index process, I get a slope of minus 0.08. So we're off by a factor of 4. But for my money, that's not all that bad. Okay. I think that's it. That's where I'll leave it for today. In this work, we provided a new characterization of the geometric ergodicity of parallel tempering. It's exploration agnostic in the sense that it tries to avoid dealing with all the details of exploration kernels. We do pay a price for that. We have to make that EOA assumption. We provide results on sort of infinite chain continuum asymptotics that are quite easy to understand. They're simple to write down. The bounds depend only on constants that we can estimate. And it matches our empirical results up to a factor of 4, and we're working on fixing that. We also provide computable finite chain bounds that actually do match the empirics quite well, but they're a little bit more opaque on what they mean. The paper's not on archive yet. Nikola is doing a mad dash to get this out as soon as possible. But if you're interested in the actual, other results that we have or the technical details, ask me for a link, and I'll make a little reminder to send you the link to archive once I've got it. I will simply end here with a little pitch for a software package called Pigeons. This is Montreal, so maybe I can explain a joke to you. My colleague Alex Bouchard-Co is Quebecois, and he came up with the name Pigeons because apparently, and you can confirm whether this is correct or not, pigeon means let's sample. Is this true?
Means what?
Let's sample. Yeah. We will sample.
Oh, wait, gee.
Yeah. Okay, good. I've got confirmation. He wasn't just lying to us. Very good. So this is our package, Pigeons. It's available at pigeons.run. It's a package for running all of the stuff that I talked about today in sort of hopefully with a simple interface. It's right now written in Julia, and it's only available with an interface to Julia, but we are working on a Python and R interface. So hopefully if those are your languages of preference, you can use those as well. That is it for me. Thank you very much.